We are talking about inverses. So we're going to define them, and then we're going to talk about what one-to-one functions are. So what are inverse functions? So they're functions that undo each other in a sense. So the notation is f to the negative 1 of x. That means the inverse of x, or of f of x. So if you think here, if we have x plus 3, the opposite of that would be then subtracting 3. So the inverse is x minus 3. So it's just doing everything you're doing in your function, but backwards. There's a couple properties they have. So the first one is if you take the composition of a function and its inverse, you always get x. So if we do the composition like we did in the last video, you'll get x both directions. And then the other one is that the function and its inverse are reflections of the line y equals x. So if you have a graph and you sketch y over x, or y equals x, there are going to be reflections over this line. Okay, so how can we use that? Here we have two functions, and we want to show that they're inverses of each other. So what we need to do is take the composition both directions and see if we get x. So start by doing f of g of x. So that's taking the g function and plugging it into the f function. So you have x minus 1 to the 1/3, all raised to the 3 because of this function, and then plus 1. So these are going to cancel, and then you get x minus 1 plus 1, which then equals x. That one works. But now I have to check the other direction as well. So do g of f of x, like this, and we're going to plug this function in to this function. So you get x cubed plus 1 minus 1 all to the 1/3, which then is x cubed to the 1/3. These will cancel, and you're left with x. So those check out. These are inverses of each other. If for some reason you got like x plus 1 or 2x or something weird, then they wouldn't be inverses. They would just be two functions. So sketching the graph. So remember, the second property was that the inverse is a reflection of the line y equals x. So I can take each of these points on this function and reflect it over the line. So if I'm here, I'm 1 away from my line. I'm going to go 1 the other direction and reflect. If we look at these points, this is -5, -3. And then if we look at this point, we're at -3, -5. All we did was switch the a's and the b's. This is going to work for any inverse function. If you're trying to graph it, you just switch the a's and b's. The reason being is we're reflecting over this line. So y equals x means you're just letting the y's equal the x's. So we keep doing this. We're going to get a dot here, and then this is going to reflect over to here, stay there, and something over here. So your reflection, or your inverse, is going to be something like this. So then how do we actually find the inverse of the function? So you're going to follow these steps. You're going to change your f of x into y, just so it's y and x variables. You're going to switch the x and the y, then you're going to solve for y. This works because when you switch the x and y and then solve for y, you're undoing everything you originally did to the function to get x. So you're in a sense reflecting over the line y equals x. So we want to find the inverse of this. Start by replacing the f of x with the y. So you get y equals 3 minus x over 4. Now you switch the x and the y, so we get x equals 3 minus y over 4, and then solve. So multiply both sides by 4, gives you this. Subtract 3 from both sides, gives you this. Multiply by -1, you get -4x plus 3. And that is your inverse. All right, same idea, a little bit harder. So try this on your own, and I'll go through it. All right, so first we have y equals x over x plus 1. Switch the x and y, so you have x equals y over y plus 1. At this point, I want to multiply both sides by y plus 1. So we'll get x times y plus 1 equals y. Now you want to distribute the x in to both of these. So you get xy plus x equals y. And this is where your trick comes in. You want to bring everything with a y in it all to one side. So I'm going to subtract this over and get y minus xy. Now you can factor out a y from the right side. So you get y times 1 minus x. And now you can divide by 1 minus x on both sides. So you get y equals x over 1 minus x. And that's your answer. Another example here. So we want to find our inverse, but then figure out what the domain is. So find the inverse first. You have y equals square root x plus 1. Switch that around to be x equals square root y plus 1. X minus 1 will equal square root y. If you square both sides, you get y equals x minus 1 squared. All right, so now to figure out the domain. This is going to come from the range of the original. So if you look at the original, this range is going to be 1 to infinity. And you can find that just by looking at the graph. So if I sketch the graph over here, it's going to start at 1 and go like this. So this is your original. So we start here at 1 and then you go up for your range. So what we did right here is we switched the x and the y, which then is going to mean this range of the original becomes the domain of the inverse. So you don't even have to find the domain. This is going to come down and become inherited by your new function. Because just looking at the inverse, it looks like you could plug in anything, but we want to take our original graph over the line y equals x. If I sketch in y equals x over here and we reflect this, we get this function here. So you can only get half the parabola of this instead of the whole thing. So our domain comes from the range of the original. So that's what this node is. So when you switch or find the inverse, the domain and range switch since you're also switching x and y. All right, so we've talked about the vertical line test already. So if you have a function, you can draw a vertical line to see, is it a function or just an expression? The next thing we're going to talk about is a one-to-one or injective function. So this function takes every element x and assigns it to only one y value. So you can't have like x equaling -2 has y equals 2 and x equals +2 has y equals 2. Every x has its own specific y. You find this by doing the horizontal line test, so going like this and seeing do you touch only once or more than once. So the same idea as the vertical line test, just with the horizontal line. So some examples. If you sketch this, look at the graph, we'll get something like this. And then the next one is going to look like something like this. And the last one looks something like this. So if we're looking at f of x, if I draw a horizontal line, I hit 2 times. So that cannot be 1-to-1. So that one's not. This one, if I draw a vertical line or a horizontal line, I'm only ever hitting the function once. So this one is 1-to-1. Here, this one would not be 1-to-1. One thing to note, you always have to check that something is a function first. You can't be 1-to-1 and not be a function. So number 1, check the vertical line test. And then second, do your horizontal. So if it asks you, like, is a function 1-to-1, it has to first be a function before you can be 1-to-1. So why are we doing both in the same day? So the only way for the inverse of a function to also be a function itself is if that original function is 1 to 1. So if we think about a couple of things, like think of if we draw like this function, this is 1 to 1. If I sketch in the line y equals x, and we flip this over, we get something like this, right? This is still a function. We can do the horizontal line test, it's fine. But say we had a parabola. This is not 1 to 1 because it doesn't pass the horizontal line test. If I draw a line horizontally like this, I hit twice, so it doesn't work. If I sketch in the y equals x line, your inverse then is something like this. This no longer passes the horizontal line test. So if your inverse is going to be a function, you have to pass both the horizontal and the vertical line test to begin with. So go on to Schoology and check your homework, but that's it for 1.5.